Good afternoon, students, physical science, energy. Today I'm recording a lecture on the universal law of gravitation and gravity. Okay, so these are things from last week that I want you to be able to know. It has our last week's essential question on there. How can I describe the motion of an object? And the most important one is the acceleration is a rate at which velocity changes. We're going to be talking a lot about acceleration today. So hopefully you remember this from last week and we can build on our understanding of what an acceleration is this week. So far, we have studied mostly horizontal motion. Today, we're going to start looking at vertical motion, or when things start moving up and down. And it doesn't take much for a person to start thinking about up and down motion to start considering gravity. So our essential question this week is, how do I describe the motion of a falling object? And Isaac Newton was a scientist and philosopher who is responsible for the universal law of gravitation. By the end of the lesson, you should be able to do these things. I put them here on this slide so you could read those later. Here is the universal law of gravity. It was discovered by Isaac Newton. He had this idea that the force of gravity would be proportional to the mass of the two objects divided by their distance multiplied together, their distance squared. So the total distance they are apart from each other squared. That was so important to this equation that they actually square this number. Okay, so it's the same thing as how the Earth is attracted to the moon. That's responsible for keeping the moon in orbit. This universal law of gravity actually applies to all objects, not just celestial objects, the Earth, the moon, the stars, but also objects here on Earth have this same universal law of gravity that is a force that applies to all objects on Earth. Okay, so here are some facts I want you to know. Oops, I'm not in present mode. Let me do that. That will break it down easier for us. Okay, so here's some facts we need to know before we move on to today's inquiry activity lesson. So gravity is the force that pulls the Earth and the moon together to keep the moon in orbit around the Earth. That was part of the universal law of gravitation. Isaac Newton also knew the force of gravity was the same between two objects. So this is Newton's third law. For every action, there is an equal and opposite reaction. And we're going to get to Newton's laws in a couple weeks, but for right now, we're just getting familiar with these ideas. We also know that an object's acceleration is directly proportional to its force and inversely proportional to its mass. Isaac Newton discovered this, and this is Newton's second law of motion for all objects here on Earth. This is true. This equation holds true that the force of an object is equal to its mass times its acceleration. We also know that gravity is a force responsible for the interaction between all objects. This is part of the universal law of gravitation and applies to all things here on Earth. Okay, so a small object, say a person or a penny, is pulled down towards the center of a large mass, the Earth. But also, the Earth experiences a pull from the small object. The Earth doesn't move or accelerate towards the penny because it has more mass. I thought the penny example from last week would help you remember the penny dropped from the top of the Empire State Building. So if you can imagine putting a penny out the side of the Empire State Building and dropping it, not throwing it down, but just dropping it, only force that would affect it would be gravity pulling it down. So the penny moves down towards the center of the Earth because of gravity, right? Well, the Earth also probably moves up so small an amount towards the penny that we can't even see it, or it's not even detectable. This is kind of the same idea that, like, if you were to get all the population of the Earth on one side of the Earth and they would all jump together at the same time, would you be able to get the Earth to move? And the the question is kind of unfeasible to do and carry out, because how do you pile up all the population of the Earth on one side of the Earth? But it is an interesting thought experiment to think about, if that amount of mass on one side of the Earth would actually cause the Earth to move. But anyways, smaller objects, some falls with less mass like us or the penny, we don't experience, the Earth doesn't experience a pull towards us in a way that we can see, but it's still there because of Newton's third law. For every action, there's an equal and opposite reaction. Okay, the next fact we need to remember, and it's more one of our vocabulary terms from this week, is a free-falling object is a term used to describe an object that is dropped and only affected by the downward force of gravity. So we're going to use this term free-falling object to describe like the situation with a penny where an object is dropped, not thrown down, but dropped, and how does gravity affect that kind of a motion? Okay, so some questions we need to be thinking about as we engage in these next few videos. Do all falling objects fall to the ground at the same acceleration? Okay, that's one thing that you should be thinking about right now. The second thing, does the acceleration due to gravity on Earth for falling objects change depending on the object's mass? So if I drop something with more mass and something with less mass, are they going to fall at the same time, or are they going to fall at different rates? What factors affect a free-falling object here on Earth? So compared to on the moon or in space, how is Earth different for free-falling objects compared to other scenarios even? Okay, so this is a kind of an age-old experiment about how free-falling objects accelerate towards the Earth. Aristotle, back in 300 BC, believed the acceleration of a free-falling object changed depending on its mass. Okay, so he was thinking that if you dropped a heavier object and a light object at the same time, that one would hit the ground first depending on the mass. Galileo, on the other hand, believed the acceleration of a free-falling object was constant and did not change depending on the object's mass. Galileo lived around the 1600s, from like 1500s to 1600s. So here's Galileo trying to explain that his different view of a free-falling object of any mass would fall at the same rate depending on if one had more mass or less mass. Okay, so he actually did this experiment, and we're going to do this experiment today. The legend goes that he would go to the Leaning Tower of Pisa, and he would drop objects of different sizes off of the side to see which one would land first. So I don't know if he actually did this, but this is how the legend goes. I'm sure he did an experiment similar to this where he dropped two objects of different masses off of the side of buildings to see how they would move. Okay, so this is the part of the activity that I want you to fill out. I'm going to give you a little bit of instruction on how to fill this out right now. For the diagram part of this table, I want you to use Google Slides to draw me what it is that we are talking about in the video experiment. So keys and a piece of paper. I want you to use, I don't even care if you make like a circle, the keys, and a square piece of paper and show me what's happening. Same thing with like a feather and a hammer. Maybe find a picture of a feather and a hammer on the internet and show me how you think those things would be diagrammed out, model how they're moving through the air, or not through the air if it's on the moon. This would be one through the air. The feather and the bowling ball in a vacuum chamber, draw me your best diagram here about how you think those things would be represented when they're moving. I also want you to make predictions about each situation. So you're just going to write which of the two objects you think is going to hit the ground first. So that's the big question here. Which object will hit the ground first, a heavy object or a light object? And then I want you to make some observations after you watch each situation, and what you observed was the same or different between situations would be really great too. This is a spot for you to make notes about what you observed and after and concluded about each situation. Okay, so here's the first one. I recorded myself, silly me this morning, dropping keys in a piece of paper from the same height. Okay, so watch this. It is 50 seconds long. See what happens. Make a prediction beforehand and see what happens, and then observe. Same thing they did on the moon. So NASA astronauts went to the moon and they did this experiment, Galileos Experiment on the moon, with something really light, a feather, and something heavier, a hammer, and they dropped the items at the same time. And I want you to start thinking about what's different on the moon, no air resistance, than on the Earth. So why these things fell, why they fell the way they did. Not trying to give too much away, but yeah, watch the video and see what happens. Okay, situation 3, same thing. This is actually Brian Cox. He's one of the youngest scientists and physicists to have been around. He does this experiment where on Earth in a vacuum chamber, so they take away all of the air, they drop a feathers and a bowling ball, and he is going to show you what happens in that scenario in a vacuum chamber without, it's a really cool video with the two items falling. Okay, and then make sure you do this after you watch all 3 of those videos. That's why it's in here again, to remind you to fill this out. There's also a Kahoot that goes with the videos. I would like for you to put your nickname here on this slide. A lot of you didn't include your nickname on the Kahoot. This Kahoot is ungraded, but if you do put your nickname here, I will know that you did it and you get kudo points. Okay, here is a slide that I do want you to fill out. I want you to answer these questions after you do the Kahoot and think about these things a little bit. I want you to think about what factors affect the motion of a free-falling object. You're going to answer this question here. And then you're also going to answer, do objects of different masses experience the same acceleration due to gravity? How do you know? Answer that right here. Okay, using evidence from your table with observations. This is kind of like you're summarizing the results of the 3 videos you watched. Okay. So the rest of this focuses on weight and mass, and you will discover from that experiment with the videos that an object's weight is determined by the object's mass multiplied by the strength due to gravity. And the strength due to gravity is also known as the acceleration of the object due to gravity. Okay, that acceleration of an object due to gravity is the same here on Earth. So we have this equation, weight in newtons is equal to the mass of an object times the strength of gravity. And since the strength of the gravity, they do newtons divided by kilograms for the units. That's because if you divide weights by mass, you would get newtons per kilogram. I've always seen it as meters per second squared. Meters per second squared is an acceleration, right? We learned about acceleration last week, and it tells you how much speed you're speeding up or slowing down. It's a rate at which velocity changes. So here on Earth, our acceleration due to gravity is 9.8 meters per second squared. I believe when you calculated the acceleration of the drop penny experiment, you got 9.683 meters per second squared, which means there was probably just a little bit of air resistance on the penny to not have it be this acceleration when the penny was dropped, that it got that you would get the answer of 9.8 meters per second squared. I did that on purpose so you would think about air resistance and how that slows objects down from and makes them float in the air compared to this 9.8 meters per second squared of something that would be like perfectly aerodynamic. Okay, on the moon, gravity is 1.625 meters per second squared. So there's a lot less strength of gravity or acceleration due to gravity on the moon. This makes sense, right? The astronaut on the moon in the videos wasn't falling off of the moon. He was still able to stand on the moon because there's still gravity on the moon. There's just less gravity. That's why when an astronaut goes to the moon, they can jump around on the moon and they feel a little less of their own weight because there's less gravity on the moon. The same thing happened, and I think the best example of this, I'm going to go all the way down to these slides, is a recent movie that came out, John Carter. John Carter on Mars experiences this jumping, and he can jump really, really far on Mars because he's experiencing less strength of gravity on a different planet. He wakes up on Mars. He doesn't know where he is. For those of you who haven't seen John Carter, the link to that is right here. So anyways, the acceleration due to gravity on Mars is 3.711 meters per second squared. So it's still way less than here on Earth. It's about a third less, right? So he'd be able to jump. He would feel less of his weight, and so his muscles are stronger, and he's able to jump because he doesn't have as much weight to compensate. The force due to gravity is not as strong. Okay, so the force due to gravity is really complicated because it causes objects weight, which is different than their mass. And that's something that I really want to drive home to you too today. So here are some problems that I would like you to solve with that equation. I want you to get some practice just like plugging some numbers in and solving an equation, because this is a really good science skill to have. So here is the mass of a textbook. It's 2.2 kilograms. Here is an acceleration. This is the acceleration due to gravity on Earth. So to do this math, you would do the mass times the acceleration due to gravity, and you would get 2.2 times 9.8. And that answer would go here, okay? I want you to see if you can solve these with this equation and exchange the variables out when you need to solve for different components. Okay, so more about the differences between mass and weight. Mass is the measure of the amount of matter in an object. It's the amount of stuff in an object. It does not change with gravity. It's measured in grams or kilograms. And if you increase the mass of something, you're going to increase its inertia as well. If you go to the moon, your mass doesn't change. Okay? So your mass is fixed. It doesn't change unless the amount of stuff actually gets lost. So like when people talk about losing weight, they're actually losing weight and they're losing mass as long as they're physically getting rid of fat through carbon dioxide release, which is a whole nother human physiology topic. Don't even get me started on that. Okay, so mass is the amount of stuff. It's the amount of matter in an object. That's really important. And it has these units. Okay, weight is different. Weight is a force. It's not a property. It's a force due to gravity on an object. It changes when gravity changes. The common units for weight in science are newtons. What we know as weight, we refer to as English pounds. Increase in weight is if you increase weight, you increase also your force due to gravity. So I believe on the last slide there was Jupiter's gravitational constant. If you went to Jupiter, that's the equations. You went to Jupiter and you experienced this gravity of 24.5 meters per second squared. You would feel heavier. You would walk around feeling heavier, like you were being decompressed, or somebody was like jumping on your back, because this is a large acceleration due to gravity, strength due to gravity. Okay, so that's the differences between mass and weight a little bit more for you. Both things are properties of matter. Both things are represented mathematically by this equation. Weight equals mass times the acceleration due to gravity. But weight depends on the mass of an object. So if you increase the mass, you also increase your weight. Okay? Here's a little bit more on mass and weight. This guy is really cool because he'll go through and ask people just like off the street. I believe he's in Australia or New Zealand. It's like just simple science questions that everybody thinks that they know the answer to. And then he actually kind of goes through and like helps them figure out the misconceptions of what they're saying and really get to the point and describe really well what they mean. So it's really interesting. And then this one too is the same guy, and this would be like an extension question, an optional video. It's why do astronauts experience weightlessness? And those two are available for you if you would like, but they're totally optional. Okay, so I believe that you're going to fill this table out for yourself to include 2 bullet points on your own side activity. And thank you very much for watching. I hope that this class is going well for you. I really loved your feedback on the Google form, and thank you for continuing to learn about science. Bye for now.